Yeah, very good morning. Shall we begin the session? Yeah, today's topic is integrity constraint. That is, what are the various integrity constraint that is available, or what are the various feedback that is used with the integrity constraint, or how we can deal with the integrity constraint. That is, how we can use the various parts of integrity constraints. So, integrity constraint ensures that any changes made to the database by authorized users do not result in a loss of the data consistency, and this also guards the accidental damage to the database. If there is an accidental damage that is done over the database, that is also managed by the integrity constraint. Okay, should I wait? Okay, all right. Let's see what are the various examples of the integrity constraint. So first one is the instructor name cannot be another. No instructor name can have the same ID because the duplicacy is available in the instructor ID. And every department name in the course relation must have a matching department name in the department relation. Each and every department name in the course relation must have a matching department name in the department relation. And the budget of a department must be greater than 0. So whatever budget that must be greater than 0. And in general, an integrity constraint can be an arbitrary predicate pertaining to the database. However, the arbitrary predicate may be costly to test, and therefore most of the database systems allows us to specify the integrity constraints that can be this can be tested with the minimum overhead. And we already use some feature of the integrity constraints also. Now we study what are the various forms of integrity constraint in this section. Now, constraint on a single relation. We are going to use the constraint on a single relation that is defined using the create table command that may include the integrity constraint statements. In addition to the primary key constraint, there are a number of the other ones that can also be included in the create table command, and that also allows some integrity constraint includes not null, unique, check, that is a predicate. So whatever the unique null, not null, unique, that whatever the constraint that is available, that is one of the part of the integrity constraint. Now, first is a not null constraint. So it is a member of all the domains, and as a result is the legal value for every attribute in a SQL by default. And for certain attributes, however, null values may be inappropriate, and consider a tuple in the student relation where the name is null. Such a tuple gives the student information for an unknown student. Therefore, it does not contain any useful information. Similarly, when we want to, or we would want the department budget to be null, and in cases such as this, we wish to forbid null values, and we do so by restricting the domain of the attribute's name and budget to exclude the null values by declaring it as follows. So this is done by declaring it as follows, that is underlying with the attributes. Now there is a name, varchar 20, not null, budget, memory 12, to not null, and the not null specification prohibits the insertion of a null value for the attribute. And any database modification that could cause a null to be inserted in an attribute declared to be not null, that generates an error diagnostic. And there are many situations where we want to avoid null values, in particular when the SQL prohibits null value in the primary key of a relation schema. Therefore, in our university example, in the department relation, if an attribute department name is declared as a primary key for department, it cannot take the null value, it cannot take as a null value. And as a result, it would not need to be declared explicitly to be not null. The next is a unique constraint. So SQL also supports an integrity constraint that is unique, AJ, AJ2, AJM. That specification says that the attributes AJ1, AJ2, AJM forms a candidate key, that is not two tuples in the relation can be equal on all the listed attributes. However, candidate key attributes are permitted to be the null values unless they have explicitly declared to be the not null. And recall that a null value does not equal any other values, and the treatment of these values may be defined over the another. And the check clause, so whenever we are applied to the relation declaration, the clause check specifies a predicate that must be satisfied by every tuple in a relation. And the common use of the check clause is to ensure that attribute values satisfy the specified conditions, in effect creating a powerful type system. For example, a clause check is used, that is budget is greater than 0 in the create table command for the relation department, will ensure that the value of the budget is non-negative. That is not positive. That is not negative. That is non-negative. That always be the positive. This is one of the example. Create table section, course ID varchar 8, section ID varchar 8, semester varchar 6, then numeric 40, building varchar 15, room number varchar 7, time slot ID varchar 4. And there's the primary key, course ID, section ID, semester and the year. Then check semester in, fall, winter, spring or the summer. That is the same thing that we are going to use. And we must use the check clause to simulate an enumerated type by specifying that semester that must be one of the fall, winter, spring or the summer. Therefore, the check clause permits attribute domain that is to be restricted in powerful ways that most programming languages type system do not permit. And the predicate in the check clause can, according to the SQL standard, can be an arbitrary predicate that can include a subquery. However, currently none of the widely used database product allows the predicate to contain a subquery. So we are using the check constraint that is available with the null values. Next is referential integrity. Suppose we wish to ensure that a value that appears in one relation for a given set of attributes also appear for a certain set of attributes in another relation. This condition is known as the referential integrity. And the foreign keys can be specified as a part of the SQL create table statement by using the foreign key clause that is used over here, and we illustrate foreign key declaration by using the SQL. Then DDL definition of a part of our university database that is also shown over here, and the definition of the course table has a declaration, foreign key, references, department. So this foreign key declaration specified that for each course tuple, the department name specified in the tuple must exist in the department relation. And without this constraint, it is also not possible for a course to specify a non-existent department name. And more generally, let R1 and the R2 be the relations whose set of attributes are R1 and the R2 with the primary key K1 and the K2. We must say that the subset A of the R1 is a foreign key referencing K1 in a relation R1. That is not required for any tuple in R2, that must be a tuple in R1 such as the T1.K1 equals to T2.alpha. Now the requirements of this form are known as a referential integrity constraints or integrity constraint that can be stated as a requirement that the set of the values on alpha in R2 must be a subset of the values on the K1. Note that for a referential integrity constraint to make sense, alpha and the K1 must be compatible with the set of the values with the various data. That is, either alpha must be equal to K1 or they must contain the same number of the attributes, and the types of the corresponding attribute that must be compatible, that must be overloaded, that must be ordered. And unlike the foreign key constraint, in general, a referential integrity does not require the K1 to be a primary key of the R1. It may be as a result of the one tuple, as a result of the same value for the different tuples. And by default, now when we say about the more general prefix, that is the department, reference the department, and this foreign key constraint declaration specifies that for each tuple, for each course tuple, the department name is specified in the tuple that must exist in the department relation. And without that constraint, it is also possible for a course to specify a non-existent department name. More generally, let R1 and the R be the relations whose set of the attributes are the R1 and the R2 respectively with the primary keys K1 and the K2. We have a subset of the R1 is a foreign key, that is a K1 in the relation R1 that is required for that every tuple T2 is in the R2. There must be a tuple T1 in the R1 such that the T1.K1 equals to T2.alpha. And the requirement of these forms are known as the referential integrity constraint or the subset dependencies. And the later term arises because of the preceding referential integrity constraint that can be stated as the requirement that the set of the values on the alpha in the R1 must be a subset of the values on the K1 in the R1. And note that for the referential integrity constraint to make sense, alpha and the K1 must be compatible set of the attribute. That is either A or the alpha must be equals to K1 or that may contain the same number of attributes and the types of the corresponding attribute that must be compatible with the orders with the alpha with the K1. And by default in the SQL, a primary reference is the primary key attribute of the reference table, and the SQL also supports a version of the references clause where the list of the attributes can be specified explicitly by using the unique constraint by using the primary key constraint. And the more general form of the referential integrity constraint where the reference column need to be or need not to be a candidate key that cannot be directly specified in the SQL. And the standard specified other construct also that can be used to implement such constraint that can describe over here. And we are using the part to form the attribute definition to declare that the attribute forms a foreign key. One is department name, then varchar 20, then references department. So whenever a referential integrity constraint is violated, the normal procedure is to reject the action that has caused the violation. That is, the transaction performing the update action is rolled back. However, a foreign key clause can also specify that if a delete or the update action on the reference relation violates a constraint, then it is also used with the relation schema. It is also used with the division. So there's a create table classroom, building, varchar 15, room number, varchar 7, capacity, numeric 40, primary key, building room number. The next is create table department. So one is a classroom, one is a department, department name, varchar 20, building, varchar 15, budget, numeric 12 to check budget is greater than 0, then primary key, department name. The next is a create table course, course ID, varchar, title, varchar, department name, varchar, credits, numeric to 0, check credit is greater than 0. Then primary key, course ID, foreign key, department name, references, department. Then the create table instructor ID, varchar 5, name, varchar 20, not null, department name, varchar 20, then salary, numeric 82. Then this is check salary is greater than 29,000. Then primary key ID. Then foreign key, department name, references, department. So this create table section, course ID, varchar section ID is used with the section ID, with the department, with the ID, semester, year, building, room number, time slot ID. System must take the steps to change the tuples in the references relation to restore the constraint. There is a create table course, foreign key, department name, references, department, on delete cascade, on update cascade. And because of the clause of the delete cascade associated with the foreign key declaration, if a delete of a tuple in the department results in the referential integrity constraint that is being violated, the system does not reject the delete command. And instead the delete cascade to the course relation, deleting the tuple that refers to the department that was deleted. And similarly, the department that does not reject an update to a field also referenced by the integrity constraint if it violates the constraint. Instead, the system updates in the department name in the referencing tuple in the course to the new tuple as well. And the SQL also allows the foreign key clause to specify the action, then the cascade will be used in the null, not null foreign key. Now, next is integrity constraint violation during a transaction. That is a part of the foreign key, that is a part of the primary keys. For example, when you say about the, suppose we have relation person with the primary key name and alternate attribute spouse. Suppose that a spouse is a foreign key on a person. That is, a constraint must have must say that the spouse attribute must contain an attribute that is present in the person table. Suppose we wish to note that the fact John and Mary are married to each other by inserting two tuples. For example, one for John, one for Mary in the above relation with the spouse attribute set to the Mary and the John respectively. So the insertion of the first tuple would violate the foreign key constraint that is used with the deferable, that is used with the conditions and the assertions. Next is the complex check conditions and the assertions. So SQL also standard also provides the additional construct for specifying the integrity constraint that is described over here. However, you must aware that the construct be aware are not currently supported by most database systems. So we are using the check clause that can be arbitrary predicate, which can include a subquery, and in the database implementation support subquery in the check clause, we specify the following referential integrity constraint on the relation section. So there's a check times load ID in select times load ID from times load, and the check condition verifies that the times load ID in each tuple in the section relation is actually the identifier of a times load in the times load relation. Therefore, the condition have to be checked not only when a tuple is inserted or modified in the section, but also when the relation times load changes, when a tuple is deleted or modified. Another natural constraint on our unit schema would be to require that every section have at least one instructor teaching the section. In an attempt to enforce it, we must declare an attribute, that is the course ID, section ID, semester year of the section, from the foreign key referencing the corresponding attributes of the teacher's relation. So complex check relation can also be useful when we want to ensure the referential integrity of the data that may be costly to test. For example, the predicate in the check clause that is used will not only have to evaluate it when the modification is to be made of the section or to the section relation. This is the create assertion, credit and constraint check not exist. Select ID from student where total credit is greater than less than select some credits from text natural join course where student.id equals to text.id, and grade is not null, grade is less than or equals to F. So what is an assertion? It is a predicate or the condition that expressing a condition that we wish the database always to satisfy. And the domain constraint and the referential integrity constraints are a special form of assertions. And we must have paid substantial attention to these forms of assertion because they are tested, applied to a wide range of the database applications. So if there are many constraints that we cannot express by not using or by using not with the special forms, and the two examples of such constraints are for each tuple in the student relation, the values of the attribute total credit must be equal to the sum of the credit of the courses that the student may have completed successfully, and the instructor cannot teach in two different classrooms in a semester in the same time slot that is the same. Let's just create the assertion name, check predicate. So this shows how the first example of the constraint can be written in the SQL. Since the SQL does not provide a SQL for all X, we construct is a predicate that we are forced to implement the constraint by the equivalent constraint that is not exist X, so that not Px can be expressed in the SQL. So we leave the specification of the second constraint as an exercise for this. Now, next is SQL data types. We already discussed this one, that is the date, month, timestamp, default values. That is for creating the table, for manufacturing the table, for using the table. Then index creation we have done, large object, user defined data type that we have done already, domains we have done. Now this is the create table extension. We are using the create table extension, that means extending the create table forms. The schemas, catalogs in the environment with how the files are named in a file system. Early file system were flat, that is all the files are stored in a single directory. Now the current file of course have a directory structure with the file stored within the subdirectories. And to name a file uniquely, we must specify the full path of the file. For example, we are using the single space file catalog schemas relation that are contained within a schema. And some database implementations also use the database in place of the term catalog. This is a catalog 5 university schema.course that also provides a SQL environment. Next part is authorization that I'm not going to take right now because time is not left for the class. So authorization we are taking out within the next class, that is the tomorrow's class. I will give you a rough idea, that is that authorization means a privilege. So till now, any doubts, anyone? Anything that you want to ask? Okay. One more thing, please submit the assignments on the time. If there is any doubt in the assignment, anything that you want to ask, then please clarify that out, because the assignment is very crucial in your course, because there is no exam, there is nothing. So assignments are very crucial by means of the grades.